Hello students. Okay, in our last class we have talked about parallel plate capacitor, and so far this is what we have learned about parallel plate capacitor. Okay, this is the positive plate, this is the negative plate. PPC means parallel plate capacitor. This is the charge on the positive plate, this is the charge on the negative plate. Okay, a battery, a potential differences of V volt is applied between both the conductors. Okay, so there will be an electric field ranging from the positive, directing from the positive plate to the negative plate. Okay, at the edge there will be some fringing effect. Okay, so this is the electric field that will exist between the two plates, sigma by epsilon naught. Okay, Q by A epsilon naught, and the potential difference between the two plates, uniform for uniform electric field, potential difference will become electric field into distance. This is the expression of potential difference, and from this expression we get the capacitance of this parallel plate capacitor, which is epsilon naught A divided by D. Because till now we are not putting any medium, we are keeping vacuum out here or air. Epsilon naught A by D. One plate is positive, the other is negative. There will be a force of attraction between them. So for a force will become Q square divided by twice epsilon naught. I'm not putting the minus sign. In the last class you have seen the minus sign. I'm not putting the minus sign here. Okay, that minus sign simply indicating your the force is attractive, so we understood that. So Q square divided by twice epsilon naught, sigma square A by twice epsilon naught. We can write it like this also, because Q can be replaced by sigma A. So sigma square A square, one of them will get cancels. And at the end you have seen, at the end of the video, last video you have seen some homework was there. Electrostatic pressure. What is electrostatic pressure? Is nothing but force divided by area. If you bring the area here, this is force. One plate is exerting the force on the other plate. How much force one is exerting per unit area of the other, that will be called as your electrostatic pressure. Okay, so in today's class we will be continuing from here, and we will be finding out the potential energy that can be stored in the capacitor. Okay, let us proceed. And what is the energy density? Okay, so now let us talk about energy stored in a capacitor. Okay, so this is a parallel plate capacitor, and across this capacitor I have connected a battery of V0 volt. Okay, suppose at any instant of time the capacitor is yet to be fully charged, is not yet charged fully. Suppose at any instant of time the charge in the capacitor is Q. If the charge on the capacitor is Q, then potential with difference between these two conductors, or between these two plates, okay, will become how much? V is equal to Q by C, right? So this is the positive plate, this is the negative plate. So if I have to put now this particular battery will keep on depositing charge here plus Q. Okay, so this battery will have to keep on working constantly against the repulsive force of the charges which are already present out there. For example, think about a conductor in which a charge of plus Q is already there. Now you want to put an additional charge delta Q or dQ. When you're trying to put this particular charge on this conductor, okay, don't you think what a conductor will do? Invite the charge or repel it? Definitely will oppose it. So if you want to put it here, you have to work against this repulsive force. Take it. Okay, similarly this battery will have to work against the repulsive force. So at any instant of time, this is the scenario, at any instant of time charge is Q, small q, the potential difference between the two terminals is nothing but B. And now we are putting an additional charge delta Q. Okay, so if dQ amount of charge is brought against the repulsion, then how much work will have to do? dW. Work done is equal to what? Charge into potential difference. At that instant, potential difference is V volt, and we are putting an additional charge dQ. Okay, and while putting this dQ is such a small amount, so the potential will approximately remain constant. Okay, right? Then work done. For example, work done by variable force. We have learned in class 11. work done by variable force. The force is changing. Force is changing with respect to position. So how do we calculate work done here? So for that, what we do, we consider a small displacement. We consider a small displacement and we assume over a small displacement, force remain approximately constant. Force remain approximately constant. So work done over this small displacement, we can write dW is equal to F into dx. So potential difference between the two plates is V. Now we are putting a small amount of charge in which we can assume the potential to be remaining almost constant. Then work done will become what? Charge into potential difference at that moment. Okay? At that moment. So this is work done. Potential difference into charge. Okay? That is. So therefore, if I have to put a charge, okay? Therefore, work done in putting a total charge Q in the capacitor. Suppose Q is the maximum charge that can be put in the capacitor, and when the charge in the capacitor becomes capital Q, the potential difference between the two terminals becomes V naught. Will become how much equal to? W will become integration of this. Let us do it like this: 1 by C integration Q dQ. So charge is grown from 0 to capital Q. Okay, so this is integration dQ. Q into dQ is Q squared by 2. So this will finally become Q squared divided by 2IC. I have put the limit. Let me show it. 1 by C, Q squared by 2, 0, capital Q. Okay, so this will become your half. C will remain Q squared, capital Q squared. This is the work done. So this work done will store in the system as its potential energy. That's the work. So you have got U is equal to half Q squared by C, but we understand Q can be written as CV also. So this expression can be written as CV naught. You can write it as CV naught. V naught is the okay. So this can be written as half C V naught square, or Q by C can be replaced as V naught. So from this expression, one of the Q and C will get replaced by V, half Q V naught. This is the expression of energy that will get stored in the capacitor. Now again, C is equal to half C V naught square. We know capacitance of a parallel plate capacitor is epsilon naught A divided by D, and V naught is equal to electric field into distance. So V naught square is equal to U square D square. One of the D getting cancels out. So we get the expression of electrostatic energy as half epsilon naught E square, area, cross-sectional area of the plates into separation. What does it give? You have the parallel plate capacitor. This is the plate area and this is the separation. So plate area into separation will give you the volume occupied by these two conductors. So therefore this is going to be your volume. So from here we can define energy density. From here you can define energy density. How much is that? U divided by volume. Volume means AD. So how much will come here? half epsilon naught E square. This is energy density, energy per unit volume within the, okay, so we have seen energy is getting stored in the form of electric field within the capacitor. Now let us find out energy that can be stored on a spherical conductor, or I can call spherical capacitor made of one conductor. Okay, better to say spherical conductor only, of radius r. Okay, a charge of q is given to this. How much energy will get stored here? Okay, though in the previous expression the energy between the two parallel plates we have got half c v square or half q square by c, though we have got this is the energy stored in a parallel plate capacitor, but this expression of energy will be correct or will hold good for any type of capacitors, let it be spherical capacitors or let it be parallel plate capacitors or let it be cylindrical capacitors. So in this particular spherical conductor, a charge q is given. Okay, then how much energy will get associated with this particular spherical conductor? So its capacitance is how much? We have done earlier, 4 pi epsilon naught r. This is the capacitance of a spherical conductor. So therefore energy will become how much? Half q square by c, or it can be written as c is equal to 4 pi epsilon naught r. So this will become q square divided by 8 pi epsilon naught r. This is the energy that will store in a spherical conductor having radius r and a charge q. Okay.